Okay, today we shall do completeness of LP to begin with. I mean, LP as a vector space we have seen because of Minkowski's inequality, and it's a norm space with the P norm. That is after quotienting this, that, whatever, these things we have seen last time, right? Where did we stop? Right, it's a normed linear space. This is where we stopped last time. It's an equivalence class of functions, and it's important to remember that you have seen that in the notes that I posted on completeness of L1 mu using something else which is not in Rudin. I'll often do that. That is, I'll stick to the theorems of Rudin, but I may not prove them all the time according to how Rudin has proved. You should know there are different ways of proving things. So I proved completeness of L1 using some other criterion, and that have in detail I have posted it in the classroom, Google Classroom. Okay. Completeness of LP for 1 less than equal to p less than equal to infinity, I am going to prove today. I'll handle the p equal to infinity case separately and 1 less than equal to p less than infinity case separately. Okay. All right. So it's a non-linear space so far. Why is it not writing? Okay. Let Fn be a Cauchy sequence in LP, of course. I mean, I'm not writing the measure mu, etc., because when we talk of LP, there is it's of course with respect to a measure mu. We have a measure space. Okay. Get a subsequence. So Fn is a Cauchy sequence, right? Usual definition of Cauchy sequence. That is, given an epsilon, you can find a capital N such that norm f little n minus f little m is less than epsilon. The norm is the LP norm here. Whenever little n and little m bigger than equal to capital M. So I'm taking epsilon equal to 1 by 2 to the power I. I'm allowed to take that. And the Cauchy criterion given on Fn tells me that if I go very far out into the sequence, my elements will be epsilon close. In this case, 2 to the power minus I close. Okay. All right. So I can do this, right? If you have any doubt about this, let me know. Now, the moment I write that I'm getting I have gotten a subsequence f and j such that norm fni plus 1 minus fni is less than 2 to the power minus I. You know what I am going to do. The choice of 2 to the power minus I tells you that I'll sum. That is why 2 to the power minus I. So I consider the function which is summation I equal to 1 to k mod fni plus 1 minus fni. Again, the series. This should remind you the criterion we did last time of completeness of a non-linear space in terms of a series. Exactly the same thing. And g equal to summation 1 to infinity this. Don't worry about g right now. worry only about GK. GK is after a finite sum, you should have no objection about it. By Minkowski's inequality, I apply Minkowski's inequality to GK. So I'll get norm GK. This is the P norm. It's perhaps good to remember that the P norm is less than equal to sum over I equal to 1 to K P norms of Fni plus 1 minus Fni. Actually, P norm of modulus Fni plus 1 minus Fni. But the moment you are talking of a non-negative function, its P norm, I mean, its modulus is the same as itself. Well, okay. Norm of modulus of a function is the same as norm of the function because the norm is in terms of modulus. The norm is integral mod f to the power p d mu. So norm of mod f is the same as norm of f. This is Minkowski's inequality. And that, mind you, is less than 1 for all k. Because, well, because of the line you can see at the top of the screen now. Okay. All right. Now apply Fatou's lemma to G. That is, G is Fatou's lemma tells you something about limin, right? So G is limit k going to infinity gk. So limit is the same as limin. So by Fatou's lemma, I mean, no, sorry, not in general. When the limit exists, limit is the same as limin. I have norm G to the power P is less than equal to limin of the norms of gk to the power P. I'm not going to recall Fatou's lemma. These have been done in your major theory class. Can someone confirm that indeed Fatou's lemma has been done and you guys are comfortable with it?
Yes, sir.
Good. So this is less than equal to 1 because the sum, that is norm of gk, never exceeds 1. That's why. So G is an LP function. G as a function is an LP function. Is an LP element. Okay. Since the norm, the LP norm is less than equal to 1, in particular, you know something, namely Gx less than infinity almost everywhere. I mean, on some null set, the value might become infinity. Who cares? But could not be on a set of positive measure because then the LP norm will not be finite. So do you notice it's a very ingenious use of Fatou's lemma to finally conclude that G is a function which is less than infinity almost everywhere. So now consider this series. So on that almost everywhere set on which G is finite, so what the hell is G? G was this. Look at the top line. G was this. So this means that summation I equal to 1 to infinity Fni plus 1x minus Fnix modulus of that is a finite sum. The series converges for almost all x. So except on a set of measures 0. So except on that set of measures 0, everywhere else, the sum is the scalar sum, the sum of Fn plus 1 ix minus Fnix That's an absolutely convergent series. Since it absolutely converges, it converges. I can add Fn1 to that because I mean it starts with Fn2 minus Fn1, and I want to cancel that Fn1. Converges absolutely almost everywhere. But what the hell is this? Okay, let us give a name to the. So f is a function defined almost everywhere. Maybe denote the sum by fx wherever it converges. Put fx equal to 0 wherever it doesn't converge on the complement. Put fx equal to 0 on the complement. Agreed? So we have a nice function, a function which fx is the sum of the series almost everywhere, and on a null set it's 0, and there the series on that null set the series does not converge. So fx is not equal to the series, but who cares? Okay, where it converges at those points, at those x for where it converges, maybe I write we have what is fx? Fx is the sum of this infinite series, but sum of the infinite series is limit of the partial sums. But isn't that just fn? I think it's fnkx because only the last term survives. It's a telescopic sum. Oh, limit. So what have we done so far? Take stock of what we have done so far in the last 15 minutes. We started with a Cauchy sequence in LP, Cauchy in the LP norm. And then we took a convenient subsequence, convenient because summation 2 to the power I converges, nothing special about 2 to the power I, any convergent scalar series would have done. And if we had taken norm n f I plus 1 minus norm f n I plus 1 minus f n I less than the nth term of the convergent scalar series, that will be fine. And so what we have finally shown in the last line is that that subsequence fnk that we found out, that converges almost everywhere. This point is worth noting separately. It's in itself it's an important useful result. This can be used in various places. Because almost everywhere is a very strong convergence. strong mode of convergence. That's why. Agreed? Okay. So we have done that. So by the way, did I write 1 less than equal to p less than infinity to begin with? That's what we are dealing right now. So we have found an almost everywhere convergent subsequence. This is what we have done so far. Given an LP convergent sequence, we have found an almost everywhere convergent subsequence. Okay. Fine. Okay. This F is obviously my candidate for the limit of the LP sequence. I have oh, not convergent. I'm sorry. Someone should have told me. Given an LP Cauchy sequence, we have found an everywhere convergent, almost everywhere convergent subsequence. Okay. Our aim is, given this LP Cauchy sequence, we must show that it's convergent. Now that means we have to find a limit. How else do we show that it's convergent? We have to find the limit and show that it goes there. Now that we have found this F, which is an almost everywhere limit of a subsequence of the given sequence, this F is my natural candidate. Give me a second. Hello. Yeah. I am in a class right now. (4:15). Thank you. Bye. Yeah. So this F is an almost everywhere limit of a subsequence. So this F is my candidate. We hope that this F will be the LP limit. So first thing that needs to be shown is this F is in LP. That we don't know yet, right? I mean, it is an almost everywhere limit, but is it in LP? So that's the first thing, that you will see that almost everywhere is such a strong mode of convergence. It will automatically imply it's in, because of the fact that each FNK is in LP. What do we know? Each FNK is in LP, and FNKs converge to F. So I have an LP sequence which converges almost everywhere to something. Then the limit is LP because of the following reason. Following very simple reason. Agreed? Again, Fatu's lemma. X is the whole measure space. I'm sometimes writing X, sometimes writing omega. I mean, please bear with me. Now, I'm given that my original sequence is Cauchy. Of course, my subsequence is also LP Cauchy, because the original sequence is Cauchy and so on. I guess I shall be able to make two just with the original sequence. My original sequence is Cauchy. That gives me this, that given an epsilon positive, norm Fn minus Fm is less than epsilon for large n and n. Fine. I look at F minus Fm. All right. So start with an epsilon, get capital N, which satisfies star, and then get a little m which is bigger than capital. Some little m bigger than capital. Doesn't matter. Okay. And I'm looking at integral mod f minus fm to the power p dv. Let's see what we can say about this. What is f after all? F, mind you, is this, as you can see at the top. Yeah. So I have replaced f by fni, and I'm applying Fatou's lemma, so there is a limit outside the integral. That's all. Now, because note that m is bigger than capital N, and I'm taking lim inf over I, ni is also large. Sooner or later, it will exceed capital N. So this, the module, this is, of course, maybe I should write it as the norm. Okay. Now apply star. Because of star, this will be epsilon power p. We are done. So f minus fm belongs to LP for, in fact, any m greater than n. So f is in LP. Okay. All right. So first of all, we have gotten f is in LP. Also, this thing, which this inequality where I have put the red tick, tells me that also norm f minus fm is less than epsilon for m greater than n, and we are done. Okay, and that is the completion of the proof. We have found the limit. So fm converges to f in LP norm. So in all these completeness issues in CX as well as in LP, the objective is to get a pointwise limit first. And if you can do any better, in case of CX, you only need a pointwise limit and you show that it's the uniform limit. And in this case, you get an almost everywhere limit of a subsequence, and then you apply Fatou's lemma to show that it's an LP. But a pointwise limit is the key. You hold on, you produce your candidate by that. Okay. So that shows completeness of LP. Now, that brings us to the question that yes, we know that LP is a I'm still within the range of 1 less than equal to p less than infinity. Okay, I have not handled L infinity yet. We'll do it. Now LP is a complete normed vector space, agreed. But you saw that its definition is considerably abstract, right? So are you really able to grab it in your hands? That's the question. Now, unfortunately not. It's an equivalence class of functions, blah, blah, blah. You can deduce stuff about it, but will it not be so much better if you could describe it in terms of nicer functions? Okay, nicer meaning what? There are two possibilities. One is if you could describe in terms of simple functions. You have seen simple functions in your measure theory class. These are just step functions. So you divide the whole space into finitely many parts, and on each part you put a finite number for the function. That's why it's called a step. It looks like steps. So one is that. Nothing can be simpler than that. That's why they are also called simple functions. The other is continuous functions. Can we get hold? I mean, everybody likes continuous functions. Can we get hold of LP functions in terms of continuous functions? Of course, so far we are in arbitrary measure space, so no question of continuity. But when you can talk of continuity, in many cases, the measure spaces are actually also topological spaces, right? Like Rn, for example, or something else. Okay. So we'll first see this simple function issue. Let's resolve that, and that's a very nice piece of gratifying piece of result. All simple functions is that the set of all points where Sx not equal to 0 is finite. Why do you need this assumption? I mean, if the assumptions bother you, think about this for a moment. That if this set had infinite measure, then we run into problem. Then these will not be LP functions, because when you integrate, you have a set of infinite measure on which the value of the simple function is something, not 0, and that makes the integration infinite. So this class of complex measurable simple functions on X is dense in LP. Now that's a very important piece of information, that you have found a dense set which really consists of nice functions. So maybe when you want to do something on LP, maybe you can do it on this nice class of functions which is dense, and maybe you can extend whatever you want to do to the whole space. Many times that is possible. Sometimes it's not possible. Then other strategies will have to be employed. Proof, for the reason for which I already explained, S is contained in LP. Well, now I'll approximate an arbitrary F from LP by such simple functions. So first, suppose F is an LP function which is non-negative, and then I'll do the general case. Okay, this you have surely seen before, but to be on the safe side, let me define En comma I is F inverse and Fn is equal to this. And maybe while we are at it, we write down the function and as well. So f greater than equal to 0 is given. F is greater than equal to 0, so it can only be in 0 infinity. And what I'm doing is, well, if this looks too abstract, Rudin writes this way, and Rudin is very precise and concise. For people like me who don't understand such difficult, concise things, I prefer writing them more elaborately. Now, if I don't have space to write. Okay. I should go up to n to the power n. That's what that Sn is, which has been written in terms of symbols at the top of the screen now. So I'm given an f which is non-negative, and if f becomes too large, I don't like it. I cut it off at n. Fix an n. Fix an n of your choice, and cut f at n. Even when f is below n, I partition from 0 to n. I partition into many intervals, and so f when the f value, so this is a partition, mind you, of the y-axis, okay, and this is the basic difference with Riemann integration. Remember this: in Riemann integration, you partition the x-axis, the domain. In Lebesgue integration, you partition the y-axis. That was Lebesgue's insight. Okay, and hence he produced these simple functions and defined integration of an arbitrary non-negative function through the simple functions. Once you are able to integrate a non-negative function, you can integrate all the way up to complex functions without any problem. So partition the y-axis, and then what happens is I have these little intervals, all joining up to the whole interval 0 to n. And when f goes beyond a certain level, I always cut down f to the lower limit. That's what you have seen here. So when fx is between I minus 1 by 2 to the power n to I by 2 to the power n, then I put the value of Sn at I minus 1 by 2 to the power n. Okay? All right. So these are simple functions. Moreover, 0 less than equal to S1 less than equal to S2 dot increasing sequence of simple functions that doesn't require anything. It's straightforward from the definition, and spend a minute and you will see that. And very importantly, Sn goes to F pointwise for all x. Why? Well, take any x, fx has some value there. Sooner or later, n will become bigger than that. N will become bigger than fx, that is. So fx is not bigger than equal to n. Fx is less than n. That means fx falls in one of those intervals which are at the top of the screen now. The moment fx is there, value of Sn is I minus 1 by 2 to the power n. Where is fx? Fx is between I minus 1 by 2 to the power n and I by 2 to the power n. Difference between fx and Snx is at most 1 by 2 to the power n. At some, okay, one of them should be an inequality, right? Yeah. So the difference is at most 1 by 2 to the power n, and you are done. Okay, so Snx goes to fx as n goes to infinity for every x, point-wise convergence. Only point-wise convergence, nothing more is being said. Okay, to begin with, f was in LP, mind you, and Sn is less than equal to f. Sn non-negative less than equal to f. F is in LP. You cannot stop Sn from being in LP. Because Sn to the power p is less than equal to f to the power p, point-wise. Integrate. Integral f to the power p is finite. So starting with an f, this sequence of simple functions that is produced, these are canonical sequence, by the way. This is used all the time in measure theory. This sequence is in sequence of simple functions in LP. Now, since Sn is in LP, is it possible that the set of points where Snx is not equal to 0 could have an infinite measure? I explained at the beginning of the proof that that's not possible. Then that simple function would not be in LP. Sn belongs to S. So given an f, we have produced a sequence Sn from the set S that we stated at the statement of this theorem, such that Sn, so far Sn converges pointwise and in LP. Agreed? Think about this last line a little. Mod f minus Sn to the power p is less than equal to mod f to the power p. Why? And leave that an exercise. Go back to the definition of Sn and see f minus Sn. How big can this be? It's really very small. That's why. So by dct, because mod f to the power p is integrable, f minus Sn is a sequence dominated by an integrable function, and f minus Sn goes to 0 pointwise. So I've approximated f by Sn. Now, of course, I hope this is clear to you. It's a very nice construction. So simple. If not, ask me now. Apart from this little y, I haven't left anything. Okay. If you are given a complex function f, any complex function f is of the form because any complex function you will first write the real part plus I times the complex part, and then real part is a difference of two non-negative functions. The complex part is difference of two non-negative functions. That's what. And now get an approximating sequence for each of them, and then form this combination. Done, right? Okay. So that is one bit of satisfying information that simple functions, nice simple functions, are dense in LP. Something to remember. Okay. There is another class of functions. I haven't yet done L infinity. I'm aware of that. We'll come to that. We are stuck to p greater than equal to 1. But while we are at it, I don't want to lose the momentum to show you what all can be done with this. The other bit of information that I want to give you is I won't be able to complete it today, but I can perhaps start it today and I'll take it up tomorrow again, that continuous functions are also dense mean. Now for that, of course, I need a topological space. And the background actually starts from before. It requires something called Luzin's theorem, which Swagato told me he could not cover. So I'll do that first, and that itself is a piece of information. So, well, Luzin's theorem follows from Igorov's theorem. Great development by Russian mathematicians, okay, because obviously everybody belongs to the Kolmogorov school. Kolmogorov was the inspiring factor behind all these people. And by the way, Rudin does not prove Luzin's theorem this way. But as I told you, I'll stick to what the statements of Rudin, but not always prove them by how Rudin proves. And in any case, you should know Igorov's theorem. Let X be a locally compact Hausdorff I was using X for measure space. Oh yeah, and it's the same, of course. Locally compact Hausdorff topological space. If that sounds too difficult, just think of Rn. Good enough. In any case, these were first proved in Rn. First proved in R, then proved in Rn. Then people realized that you can generalize these two locally compact Hausdorff topological spaces. And that mu, so you have a locally compact Hausdorff topological space, so you have the Borel sigma field, which is the sigma field generated by the open sets. And let mu be a regular measure on the Borel sigma field. Yeah. By the way, I hope you understand, all of you understand what a regular measure is. I need those regularity properties, like it's exactly the regular measure that Rudin defines. That is approximation by compact sets from inside, approximation by open sets from outside, and so on. If you're not comfortable with those, speak up now. These are properties of the Lebesgue measure. And then they were kind of abstractified and one made a definition. And again, it's good enough to think of Rn with the Borel sigma field and Lebesgue measure. Suppose E is a set of finite measure. Let Fk be a sequence of measurable functions such that Fk goes to F almost everywhere on E. Fk is a sequence of measurable functions so that Fk goes to F almost everywhere on E. And mind you, the hypothesis is just that Fk almost everywhere convergence is even weaker than pointwise convergence. Okay, it says that there is a null set on which you don't know what happens. Remarkable conclusion. So you only started with an almost everywhere convergent sequence. Okay. And of course, you will tell me, well, what is the big deal about almost everywhere? You only have a null set on which it doesn't converge. Throw away that null set. Fair enough. You throw away that null set from E. So without loss of generality, assume that Fk goes to F everywhere on E on a set of finite measure. This finite measure is important. Okay. But then look at the conclusion. You only have pointwise convergence, right, on E. And it says that there is a closed subset of E such that the closed subset is very big. I mean, you could find a small closed subset on which the convergence is uniform. What's the big deal? But the closed subset is very big. The difference in measure is less than epsilon. Given any epsilon, you can get a closed set. What I have not done is I should have really written a suffix epsilon to remember that the set A depends on epsilon, but that clutters things too much, I thought. So remember that A depends on epsilon. So given an epsilon, you can find a closed set A such that the A is so big that E minus A, the remaining portion, has measure less than epsilon, and Fk converges to F uniformly. Now this is as good as it gets. Okay. Okay. Let me see how far we can go. I have to attend a talk at 4. So today, I mean, on some days I teach 5 minutes extra, but today I might have to leave, in fact, 2 minutes early or so. Let's see. So replace, for the reason that I've already explained. No, don't replace anything. I'm just. Without loss of generality, assume Fk goes to F everywhere on E instead of almost everywhere. Fk goes to F on E. Why? Again, the reason is there is a null set N contained in E such that except on N, Fk goes to F, Fkx goes to Fx for every x in E minus N. But then now replace E by E minus N. Mu of E minus N is less than equal to mu of E, which is finite. So mu of E minus N is also finite. So replace E by E minus N. Without loss of generality, assume Fk goes to F on whole of E. Now, by the way, this proof is from Stein and Shakarchi. Stein and Shakarchi has a 4-volume book. This is in the volume which says real analysis. Okay, page 33 or so, if I remember correctly. But Igorov's theorem is so famous, you will find it everywhere. Fix an N. Fixing an N, call ENK to be those X such that mod Fjx minus Fx is less than 1 by N for all J greater than K. Okay. This is of course contained in E. Note that for fixed N, En1 contained in En2, contained in all of them contained in E. And why is that so? Why is ENK contained in ENK plus 1? Just look at the condition. ENK will have this, at this place, it will have K. ENK plus 1 will have K plus 1. Now, if it's satisfied for all J greater than K, it will, am I saying the correct thing? All J greater than K. Just give me a second. Yeah, all j greater than k. And if you take a j greater than k plus 1, that's all. That's of course greater than k. I guess I'm saying the correct thing. Yes. I don't know why I'm confused. And ENK actually increases to E as k goes to infinity, because Fk goes, the sequence Fk, Fj, the sequence Fj goes to F everywhere on E. Okay, so it's an increasing sequence of sets going to E. So mu E equal to this is measure, because mu is a measure. So there is a Kn such that mu E minus ENKN is less than 1 by 2 to the power n. This is because the measures of E and K are increasing to the measure of E as K goes to infinity. So sooner or later, and well, there's an increasing sequence of sets. So if you look at E minus ENK, this is a decreasing set, a sequence of sets for which the measure is decreasing to 0. That's why. Okay. Remember, mod fjx minus mod fx is less than 1 by n whenever j greater than kn and x belongs to enkn. X belongs to enkn means, by definition of enk, that mod fjx minus fx is less than 1 by n whenever j greater than kn. This, look at the definition of enk at the top line. I really hate to leave this in the middle, but choose n so that summation n equal to n to infinity 2 to the power minus n is less than epsilon by 2. Let a tilde equal to this, then I'll stop here, and I would request you to go through this proof. I'm sorry to hurry through this. Tomorrow, right in the beginning, we shall go through this again, every step. But I understand that it's not easy. It's a typical example of a complicated major theoretic argument. Please go through this, spend half an hour on this, everything will be clear. Everything is written here. I shall share the notes today in about an hour with you. What we did is, first of all, we considered these E and K sets. Okay, check first that they're in increasing sequence of sets, increasing all the way up to E. It's pretty easy to see that their union cannot fall below E. So the measure increases to the measure of E. Consequently, find for every n, find a number kn such that mu of E minus ENKN is less than 1 by 2 to the power n. And again, as you see, this sequence 1 by 2 to the power n is omnipresent in measure theory, because you need to sum. And you, I mean, as I said, all you need is a summable series. This 1 by 2 to the power n is nothing special. Okay. Find a large number capital N, so that the tail of the series, sum from n capital N onward, sums to less than epsilon by 2, And then this is a smart definition of this set A tilde. This A tilde is still not closed, need not be closed. We need a closed set. We want a closed set. But this A tilde already has the property that it's very close to E. The difference in measure is less than epsilon by 2. And we shall show that on this A tilde, the function series actually converges uniformly. I shall show that in the beginning of the next class. And then still one more step remains, namely approximate A tilde by a closed set. Now this is possible because that's where you will need a regular measure by a closed set from inside. Okay, stop today. Any question?